Let's go through a problem-solving strategy that you need to use whenever you're encountering these rotational dynamics problems. First, part of your modeling is that you need to model the object as a rigid body. This means that its size and shape matters. This is the opposite of using the particle model. You need to draw a picture, and the picture you might want to choose is what I would call an extended free body diagram. It's like a free body diagram, but it's showing the location and direction of all of the forces. If you don't actually think that you need to do that because you have a torque provided or you don't actually have individual forces, then you still want to draw a representation that labels all of your variables, defines your coordinate system, etc. So extended free body diagram is usually the way to go, but not always. So make sure that you're doing these things listed here though. So identify the axis about which the object rotates. So that's defining the pivot point. If you're not showing what your pivot point is for a rotation problem, that's a huge mistake. Identify their forces and their distances from the axes. Again, this would be an extended free body diagram. So when it says to draw a free body diagram, again, it's different than before because it's not a particle. Identify any torques, if you can, and the signs of the torques. And just like before, if you know that there's a net force or if you know that there's a net torque, label that off to the side. You are then going to be able to relate the torque to the angular acceleration using the moment of inertia. You're possibly going to need to calculate the moment of inertia, or you can look it up based on the table, or you might be able to use the parallel axis theorem. Again, you've possibly needed to calculate where the center of mass is located to even make it this far. Finally, you can use rotational kinematics to find the angles and angular velocities, and this is just like the rotation stuff we did before with angular speed omega, theta, angular acceleration alpha. As always, check and make sure that your units are correct. This is even trickier with rotational problems. Just like before, when we had a constant force model, we now have a constant torque model. In our constant torque model, we have a rigid body, so it's not a particle, and we have a constant angular acceleration. So constant torque relates 100% to constant angular acceleration. If you do not have a constant angular acceleration, then you can't use the equations that we've even been looking at. You'll need to take into account constraints due to ropes and pulleys, which we'll talk about next. And then mathematically, we have a new version of Newton's second law, which is just like the old one, which was F equals ma, but now it's tau net equals our moments of inertia times angular acceleration. So this will work if you have a constant net torque, which is causing a constant angular acceleration. We will have a different model that you use when you have no net torque, so it's an equilibrium model. We'll talk about that in the next section, I think. And obviously, this is somewhat of a simplification, that if these forces are varying just a little bit, then our torques will vary. But just as we said, we're going to approximate most forces as being constant if they're even close to constant. Similarly, we're going to approximate most torques if they're close to constant as being constant, since we then can mathematically work with them.